Great. Okay. Yeah. So I'll get right into it. Where Roman left off from a kind of a theoretical background. So what we're going to do is walk through a hands-on example of actually exploring some hyperparameters for a simple model, which is just fully connected layers, small network doing the MNIST classification task. So from here on the repo, this is the top level of day 3 or session 3 rather for distributed hyperopt. So if you go into this 01 basic HPS, this is where we'll be for the rest of our session. So go ahead and scroll down here. I'll make a note that we're using a module of DeepHyper that's set up for the Theta KNL nodes, not the GPUs. So if you want to follow along, make sure that you get onto a Theta login node as I am over here. So get yourself onto the regular Theta login nodes. It'll be Theta login 4, 5, or 6. And then go ahead and get into the either clone or CD into your existing SDL AI workshop. So what we'll do in here, as Taylor mentioned, let's just everybody do a git pull just in case. See, I also had something new pop up, so git pull to get yourself up to date. And then we'll go into today's session. So navigate to this subdirectory, which is the basic HPS. So basically, when we're using DeepHyper, there are 2 key objects that we provide. It's a framework that runs code that we've written for us, right? So what we provide to DeepHyper is essentially, when we're doing hyperparameter search, a black box function, which takes those hyperparameters, builds and trains a network, and returns some validation score, which is the metric that DeepHyper optimizes. So DeepHyper really, at least in this sense, you can think of as a black box optimizer. So we're going to provide what we call a run function here, which is representing the metric that we want to maximize over our hyperparameter space. And then how do we define a hyperparameter space? That's done with the problem object. So we'll have another file where we define a problem, which is easy to do with a class that we can import and derive. And this class instance lets us basically create a set of hyperparameters and define their bounds. So for instance, we want to search learning rate. I can define a learning rate hyperparameter and set its bounds. And I'll show you how we do that later on. But so that sort of should give you a bearing of what all these files are. We have this model run function and defined in this file, the model run.py. And then we have this problem.py, which will contain our problem definition. So those are really the 2 key ingredients that are common to every run in DeepHyper, is the model and the problem. So to actually use this, we can set up a workspace here. And I would advise you to basically follow what's going on in this box. We have a module set up to use DeepHyper. And for the execution backend, we're using a workflow manager called Balsam. That's installed already in the DeepHyper module, so we don't want conflicting versions. So what I'll do is basically run this module unload Balsam command here to make sure I don't have any conflicts there. And then I'll go ahead and load this DeepHyper /0.2.1. And that will get me the environment that I need. Now, if you've been doing workshops here before, you may have already a Balsam configuration in your home directory. We want to, with this new version of Balsam, make sure that we just take the default settings for now to avoid any possible conflicts. So I would suggest that you just remove your Balsam settings, the .balsam in your home directory. And as soon as you start using it again, Balsam will repopulate this directory with new default settings that are sort of safe and guaranteed to work with the module that you've just loaded. So basically we'll go down and yeah, so we've already pulled in our latest changes. And to start working, we will create a Balsam database where we actually store all of the tasks that we want to run. So we'll put the search job into a Balsam database and let the Balsam workflow manager run it for us. And the search itself will actually leverage the database to dispatch new evaluations as the Bayesian optimizer chooses new configurations to evaluate. It actually sends them into the Balsam database, and those in turn launch onto other compute nodes. So it's kind of the hub where all of our work is being orchestrated. And we do that by typing this command balsam init. So this subcommand initializes a new database. And I'll do that here at a path. Let's say I'll call it, well, I already have a DB, so maybe I'll call it DB test. So you can name it however you like, and it will create a directory there. So you can see here, it's doing a lot of work here, setting up a database under the hood. And then if everything worked there, you should see this text that says use source balsam activate to begin working. So this command then starts up the database server and sets our environment variables up so that we can actually add jobs to the database. So I'll do that, and then I can see server started here, and that all looks good. And I have, you can see here, basically a decorator on my command prompt that shows the currently activated database. So before we go any further, it'll be really good to make sure that we have all the data downloaded in our home directories. So the compute nodes don't have internet access. So for that, we have actually, we've sort of split out the data loading into a separate file. So this load data function in loaddata.py actually calls out to the Karist helper function to grab the MNIST data set if you don't already have it. And this is actually a little bit of a helper to our model in that it shapes the data and does the split of training and test data that we're going to actually use to perform our evaluations. So we take basically the 60,000 training examples, we shape them like this, is 784 because the images are 28 squared, which is 784. And we basically return this tuple, which has both the nested tuple for the training set and the test set. So if I run this, you'll see that all it does is load the data. So you want to go ahead and do this one time on the login nodes to make sure that you've actually pulled the data in so you don't have any problems when you start the search. So I'm running it here. You can see I get some noise from TensorFlow, and then I can see that the shapes are printed correctly. So I've got the data. And one thing you can do to avoid all of these warnings from TensorFlow is export this environment variable here. So this TF C++ min log level, if you set it to 2, you'll still see errors, but you won't see all the extra warnings and infos. So see if I run again there, I should avoid any noise. And there I just get the normal output. So that can be a little handy trick when you're using DeepHyper from the command line. So then let's look at the model that we're going to optimize. So model run is where we're actually building the model, training it, and returning a validation score that DeepHyper will optimize. And the key thing to understand here is when you're taking, suppose you have a model code that you run on your own with some script, how do you adapt that to run with DeepHyper? The key is that you define a run function like this in your script, and it needs to take one parameter, which is the hyperparameter configuration, basically, this point. This point object is a dictionary which contains all of the hyperparameters passed in from DeepHyper. So it's up to us to restructure our model a little bit so that this run function takes the point, inspects the dictionary, and configures the training, configures the model according to the parameters in that dictionary. So there's not a whole lot of magic here in the sense that you need to kind of go through and do this yourself. So in our search, we're going to be looking at a dense neural network with 2 hidden layers. So here are some of the hyperparameters that we have here. We've got the number of units in the first hidden layer. We're going to call that units 1. and that's an integer value. Units 2, same thing for the second layer, is another integer value. We'll be able to choose the activation function, and that's, like Romit mentioned, that's not really an ordinal, value. So this is a string, so it takes some, basically a list of possible categories is what we're going to provide when we define this. So when we choose our activation function, we'll get one of those values passed in as a string. We'll have dropout probabilities. So actually we get 2 here, dropout 1 and dropout 2, which are applied to the first and second hidden layers respectively. A batch size, learning rate. So in this case, a good practice when you're dealing with a value that has a very large dynamic range, such as learning rate, is to use, to consider the exponent of the value rather than the value itself, right? Because DeepHyper is going to sample these floating point parameters kind of uniformly. If you search learning rate itself on the interval of 0 to 1, then 90% of your values are going to be above 0.1, just because it's a simple uniform distribution there. Well, you really want to explore, 10 to the minus 2, 10 to the minus 3. So in that case, it makes more sense to use a log scale. And the way I'm doing it in here is to just pass directly the log 10 of the learning rate. For the optimizer, again, we have a choice of optimizers. We can use different techniques here like Atom or stochastic gradient descent. And then the interesting thing about this last parameter is that we're using momentum only when the optimizer is SGD. So if we're doing SGD with Keras, then we want to pass this additional momentum hyperparameter. And this is an interesting feature that DeepHyper provides now. This is a relatively new feature in that you can set up these conditional parameters where you'll only explore something conditioned on the existence of another parameter or another parameter being equal to some value. So again, the first thing our run function does is load the data. So this is our helper function that we just tested out on the command line. So we're going to pull it in, and we're going to split out 10,000 examples for our validation. We're going to train for 10 epochs. And here, all of these point.gets is where I'm pulling out parameters that I actually need from that hyperparameter dictionary. So for instance, I get the learning rate. If it's not none, then I'll exponentiate to get the actual learning rate. I'll build the optimizer here with this helper function. So get optimizer takes the optimizer ID string, learning rate, and momentum optionally. And you can see here there's a branch. So if we're doing SGD, then we pass in this momentum. Otherwise, we just grab the relevant optimizer and pass the learning rate here. So that's sort of factored out at the top of the module. And then once we've got all of these parameters and our optimizer, we go ahead to actually build the model. So you can see here we're building this Keras.sequential model with dense layer and dropout, another dense second hidden layer with the second dropout value, and then finally the output layer has 10 units for the 10 digits. We go ahead and compile our model. So in this case, we're setting up the optimizer that we've created, setting up the metrics, and then performing model.fit on the. So we're doing the training with our training data. Batch size is yet another hyperparameter that comes in at the end here. And then for the validation data, again, we're passing through the split out 10,000 examples there from the beginning. So what we do at the end of the training for its 10 epochs here is we want to return something. So we perform model evaluate with the testing data. And what this gives us is basically a test loss and a test accuracy in a tuple. And what we want to return here is the test accuracy. So our run function returning this score 1 is returning basically the metric that DeepHyper sees. So all of this code is completely opaque to DeepHyper. It doesn't know anything about how you're building the model. how you're treating the hyperparameters. You could be even ignoring some hyperparameters that DeepHyper gives you. This is all in your domain. The key thing is this interface where the hyperparameters come in, the black box function runs, and then it returns the score at the end here. So this test accuracy is going to be the key thing that DeepHyper tries to maximize by exploring different values of the hyperparameters through this acquisition function over the random forest model. So that's maybe a lot to take in at once, but it's all set up to run. So we'll go ahead and launch this after I show you how the problem is then defined. So you could see that run function was set up to take in a point. But again, we use our problem, which is defined here, to actually specify what does a point look like, what ranges can the values take. So here in problem.py, the key thing that we do is we import the HP problem class from DeepHyper.problem. Now, this class, we create an instance of it here at the top, and then we start to add all of our dimensions for the search. So you can see here that we do problem.addDim. And in this case, for the number of units in the first hidden layer, we'll say it could vary between 1 and 64. Now, the type here is actually really important. If you pass in a tuple of 2 integers, you get basically an ordinal hyperparameter. So it can only take the discrete values from 1 to 64 inclusive. If you pass a pair of floating point values, like we do with dropout, you actually get a continuous a real number in that range. So we'll do units in both layers, the dropout in both layers, batch size, the log 10 of the learning rate. We're going to vary learning rate from 10 to the minus 5 to 1 here by setting up our exponent that way. And then we'll add a dimension for the activation function. You notice here that this is a list. So activation function can be the ReLU or a hyperbolic tangent or any of these. And then the optimizer takes, again, a list of values from Atom, RMSProp, SGD, and Atom and Adagrad. And then finally, the momentum, which is conditional on, if you remember, we're only really using momentum if the optimizer is SGD. That's where it comes in here. So you can see that we add momentum normally using this addDim, but then we use this equals condition, which is coming from config space at the top. So config space lets us add a condition where basically we only want to sample momentum if the optimizer is equal to SGD. So that's how we can set up these conditional parameters. There's a lot more you can do with config space, and that's an independent package. You can go look at config space documentation for details there on setting up a more involved search space. And then finally, we want to set up a starting point. So we will typically start the search with some randomly chosen values that seed the acquisition function and allow us to basically start honing in on more interesting points after we've sampled the landscape a little bit. But sometimes we have reference values that we know ought to work well. We want to try them first. So we do that by calling this problem.addStartingPoint. So addStartingPoint lets us specify values for all the hyperparameters that make sense to us. Maybe we want to evaluate them first. And so the search is going to start with this configuration. I'm going to use SGD with a momentum of 0.5. Learning rate is going to be 0.001 with a ReLU activation, no dropout, and so on. So if I run this problem.py, it just is going to print the problem specification here. So you can see I get some output here. Activation is categorical. Notice batch size here, uniform integer. Dropouts are uniform floats. So this is kind of showing us the configuration as it's been parsed by this problem object. So with that, we've really gone over the two key items, right? We have our run function that we've looked at. that does the training and evaluation of our neural network for the MNIST challenge. And then we have our problem space. So now we're actually ready to go ahead and run this. So yeah, so that's what I've just gone through here, the defining search space. Again, there's a link to config space documentation here. So I would urge you to go there if you have more involved needs in setting up your space. And finally, we get to launching the experiment. So because we're using Balsam already, it has some convenience functions built in to basically interface to the Cobalt scheduler, auto-generate a job script, and submit it on your behalf. So we don't actually need to type qsub at all. What we're going to use is this shorthand DeepHyper Balsam submit. So this Balsam submit basically allows us to define the experiment that we want to run and the parameters that get passed through to Cobalt. So my first parameter here is HPS because I want to run a hyperparameter search. I'm going to name the workflow, or basically a top level directory that's going to hold all of the results. So I'll call this MNIST demo 1. And then with the -p, I specify my problem. So I've got my problem.py -r to my run.py. So basically these two modules will respectively need to contain the problem object and the run function. DeepHyper will detect those and use them in its search. And then the rest of the parameters here are basically passed through to Balsam. So let's run for 20 minutes on the training queue, the workshop allocation, and then this job mode is something that Balsam uses to control how jobs are launched. This is maybe an implementation detail you don't need to worry about too much. But by using MPI, Balsam is going to app run each task that it runs. So let me actually use here, let me run this on 4 compute nodes. So I'll do N4. Let's see, so now it's submitting. DeepHyper does a little bit of validation that it can actually find your problem and your run function. Everything looks good. And then you should see this message that says success. The search will run at this directory. So this directory is where basically it's going to get auto created by Balsam, and DeepHyper will run in there. So once we've gotten to this point, we want to sort of monitor where things are going. I can always do qstat to see that my job is still waiting in the queue, but I can also use Balsam command line tools to track what's going on with the workflow. So if I use Balsam ls, I can actually see that this MNIST demo search job that I created is in my database. So it's using this application called AMBS, which is going to run the asynchronous model-based search, and it's going to run it with our parameters that we've passed through here. So if I want to kind of keep an eye on this, I can maybe do watch qstat. So here I'll just wait for my job to start. So watch will just do qstat every 2 seconds. So here I'm pulling qstat, waiting for my job to start running. It's still starting up here. Okay, so now my job, I can see, is running. Now that the Cobalt job has started, it'll take a little bit of time for Balsam to start up, launch DeepHyper, and then DeepHyper, as it starts running, will sample our configurations and add them back to the Balsam database. So I may watch Balsam ls now. And now I can see here that AMBS started running. So now DeepHyper has actually started. And this is the key point. When you see that your task has started running with Balsam, a directory for it has been created. That directory now exists. Something is running in there. And so I can jump inside and see what's happening. And a little convenience there, that Balsam provides is this BCD command. So by doing source BCD and copying in the first few or the entire string of the job ID, in this case, I only have one job, so I can just type in my case, it starts here 783. And then that immediately jumps my terminal into that directory. So I could have also copied and pasted this directory here. This is the exact same thing that you see up in purple as what I just did by the BCD command. So, and then if I look inside, you can see that I have a log file from DeepHyper, and then in the output file itself, but this is the standard output. So if I look at deephyper.log, you can see, oh, it's already started. And Balsam has discovered that I asked for 4 compute nodes. So there's 4 launcher nodes. Total number of workers here you can see is 3 because 1 node will be reserved for doing the searching. That will actually run the random forests and update the acquisition function. And then the other 3 nodes are available to run my MNIST model over and over again. So we'll have 3 going there in parallel and then 1 doing the search. So that's the nice thing about using DeepHyper with Balsam. I can just ask for an arbitrary number of nodes, and DeepHyper will know that, okay, I can do this many evaluations in parallel, and it basically ensures good load balancing, that all the compute nodes are staying busy trying new configurations of your hyperparameters. So it's a really easy way to scale out on Theta. You can see here it's finding the right Python to use, setting up an application to actually run our run function. It echoes the problem space that we've already seen. And then look here, this is really the key point. Generating 3 initial points is where, okay, it's starting from scratch and it's dispatching the 3 very first hyperparameter evaluations. So this first one is the initial point that we asked for. That's going to be a new job in our database called task 0. And then it's creating 2 others that are drawn sort of randomly here. So I've got tasks 0, 1, and 2. And I can actually see those if I do Balsam LS again. So let me type Balsam LS, and I can see, oh, look, task 0 is still running, but tasks 1 and 2 have finished. And to take the place of tasks 1 and 2, 2 new ones have started, 3 and 4. So in this way, DeepHyper is constantly running. As soon as an evaluation is finished, it's going to update the surrogate model and draw the next point from the acquisition function, and then launch them through Balsam again. So if you do something like watch Balsam LS, you could basically see these things finish in real time. So here I've got 3 finished evaluations and 3 running, and it goes on and on here. So once some evaluations have finished, I can actually go look at them. So what I'll do is in this directory where the search is running, the main job, I can cat this results.csv, and I get a nice CSV file summarizing the hyperparameters. And then in the second to last column is the objective value. So I can see my initial point started out with an objective of 0.60, so an accuracy of 60. And then I got lucky on the second one and I got a 95% accuracy. And the last column there is the elapsed time in the search. So the first result came 79 seconds into the search. The second result was 89 seconds. So another way you can follow this is just use the tail and basically follow the results as they come. So what you'll see here is initially an exploration. So the acquisition function in the beginning is sampling different values of the configuration space to basically visit those regions where the variance is still high, where it's uncertain what it's going to get. And eventually it will hone in and you should see some convergence to a region of hyperparameter space where the model is doing the best. So in this case, you could see that we're still bouncing all over the place. going from 90% accuracy down to 50, back up to 80, and so on. But that's the gist of it. So this is really how you run experiments and keep an eye on them with the Balsam command line tools. I would encourage you to look at balsam.readthedocs.io for additional basically tips for using the Balsam command line interfaces and so on. So with that, I'll hand it off to Sam, who's going to be talking about how we can actually make some sense out of these results once we have them.